I think the more demonstrations we do in the field, the more, publicity gets out. People get more acquainted with the technology. And I think people are getting more knowledgeable on batteries and what chemistries are doing.
This is EnergyCast, and I'm Jay Downhauer. Today we're talking about alternatives to lithium-ion batteries, particularly when it comes to stationary storage. Lithium is a rock star when it comes to energy density. If not for its light weight, electric vehicles might not be possible. But I've been saying this for some time now. We're asking a lot of our lithium, and it's still early days. I say, let lithium rule the roads. When it comes to stationary storage, and I primarily am talking about the utility scale variety that we hope to back up renewable energy, weight isn't that important. These big batteries are going to sit on the ground. My panelists today have 3 battery technologies that are strong contenders. They're affordable, reliable, and most importantly, abundant. If the last 2 years has taught us anything, it's that some critical supply chains might be better off closer to home. The supply chain to build a single lithium-ion battery pack stretches across the globe. My guests say their batteries' raw materials could be sourced wherever they're used. That's not to say these companies don't have challenges proving their advantages to lithium. Again, it's still early days. Even with stationary storage, there's still enough lithium to supply these projects, and many developers simply go with them because it's easy. But as we add more renewables and more distributed energy, there will have to be alternatives to lithium. And the sooner we start exploring and developing these easy-to-find alternatives, the faster, I believe, we will be living in a land filled with bountiful batteries. My guests today represent 3 battery developers. Dan Lambert is the Senior Product Manager for Zinc 5, based in Oregon. They have a nickel-zinc technology. Ed Porter is the Business Development Director for Invinity Energy Systems, based in London. I profiled Invinity and their vanadium flow battery technology in episode 89. And finally, Gautam Yadav is the Director of Advanced Battery Development for Urban Electric Power in New York. They have a zinc-manganese technology very similar to the AA batteries you might find at home. The panel was recorded for my PowerGen Plus virtual series, my last of 2021. One of the big ideas I wanted to drive home was how abundant and sustainable are the materials found in these batteries, and how much real attention and traction are they getting with storage project developers. Have lithium batteries simply sucked up all the oxygen? We'll find out. I hope you enjoy my panel, Breaking Through the Electron Ceiling, Alternatives to Lithium-Ion in Stationary Storage. Hi, everybody. Jay Downhauer here, host of the EnergyCast podcast. We're now in our 5th year, and anyone who's listened to my podcast knows I'm a big fan of energy storage, not only as a complement to renewable energy, but also as a way to streamline the energy curve for the entire grid, helping our baseload generation run longer and stronger. And I also want to point out that the podcast really doesn't pick sides. I'm a strong supporter of all energy technologies. What I like to focus on most is ways to make them stronger. But I also like to show that we should never rely solely on any one energy technology. And when it comes to batteries, it's lithium ion for everything, right? Cars, backup generation, even home electronics that used to just take 2 AA batteries. Remember that? Are we asking too much of our lithium? I can't help but think that we might be, especially when it comes to stationary storage, which doesn't need a wide energy dense battery. It sits on the ground. There's also questions about supply chain, cycles, and affordability that make our guests today and their alternative battery technologies very compelling. We'll kick it off with Dan Lambert, Senior Project Manager for Zinc 5. Hey Dan, what's going on? How are you?
I'm doing great, Jay. Thank you for the introduction. Zinc 5 is a manufacturer of nickel zinc battery chemistry. The primary things that you need to know about nickel zinc are that we are a power dense battery, very high power capacity. We are very green, and that's a big thing to a lot of people today. We've been operating this battery now for over 10 years in extreme temperature situations, unregulated generally, intelligent traffic type applications. We recommend that you use temperature compensated charging, but we've used the battery in anything from minus 20 degrees C to plus 50 degrees in a data center, and stationary energy storage type applications want to operate somewhere in the 20 to 35 degrees C. As I said, it's safe. The UL was not able to set the battery on fire no matter what they did to it. The primary metals used in it are nickel, zinc, and some copper. They're all common, widely available on all continents. The great story about this battery is recyclability. We already have an existing recycling stream right now. We don't have to wait for that technology to be developed. We are able to take a battery to a qualified recycler today and be able to return more than 90% of the materials in the battery into the recycling stream and reuse them. Lithium, they claim 50% recyclabilities. Right now in the lithium world, they're looking at maybe 50% on the few batteries that are actually recovered, but there are very few of them actually recovered. Most of them are actually going into storage for later recycling once they develop a technology. And lead acid, although it's a great recycling story, that's only true here in Western Europe, North America. Most of your third world countries do not have nearly so good a record with recycling of lead acid, and more people are poisoned by lead than just about anything in the world. In looking at the various battery technologies, lithium, lead, and the nickel batteries, the sustainability score on our part was about 9.4 out of 10, which means that of all of the batteries, we are 4 times more environmentally friendly compared to lead acid and 6 times more environmentally friendly as compared to lithium. The carbon payback times, the amount of volatile organic compounds, the water usage, the energy usage, and everything else leads us to have a 400% greater carbon payback time for lithium and lead batteries than for nickel zinc batteries. So quite a good story there. That is the end of my section. I know there are going to be a lot of questions. And so folks, bring them on.
You bet, Dan. That was great. And what a great point on the recycling. That's one of the big things that I always talk about with lithium ion. We'll get into all of that in just a second. Next, we'll go actually across the pond. Ed Porter, good evening. Business Development Director for Invinity Energy Systems. So tell everyone where you are, Ed.
Yeah, welcome to not sunny London. The sun has set, but I can break with tradition. I can tell you it's not currently raining. So it's a nice twist in the story. So here to talk about alternatives to lithium ion. I think one of the key things in talks like this is to really try and center in what is deployed, what is real, what can you look at, what can you poke, what can you touch. The factory, always would recommend not doing too much of that, but certainly, what is real. And thanks, Dan, for your talks. I think it was a really good description of the testing and the realities of sort of battery storage today. Moving on to kind of what a vanadium flow battery looks like. In reality, the system itself is really, really simple. We've got the tanks, they hold the electrolyte, that is a solution of vanadium. You can see the pumps, that pumps the electrolyte into the stacks at the top. The stacks are a series of membranes, and you can run a voltage across those stacks, and you can charge or discharge your electrolyte that way. Electrolyte then comes back down into those tanks, and that holds the charge. Really simple, really straightforward energy storage. The thing that underpins all of this is that vanadium in that electrolyte solution is stable in 4 states from B2 to B5+. The electrolyte, when being charged and discharged, doesn't suffer any degradation in being charged and discharged. And that is a really, really important thing, because it's fundamentally different to the lithium system that you would see today. You don't have any degradation in cycling, and you don't damage that electrolyte. So at the end of life, that electrolyte is still there, and you can put it into another system where you can recycle it. So to talk a little bit about where lithium works really well and where things like vanadium work really well, because Jay was absolutely right at the beginning that lithium does some really good jobs in the market. And so in terms of doing ancillary services for shorter durations or a limited number of cycles, it's really effective and has been built out in massive quantities. Vanadium is a fundamentally sort of different technology in terms of a longer duration and higher utilization energy storage type. It can handle longer durations from 1 to 12 hours, but it can also handle 2 cycles a year. I really wanted to center this in examples of where the tech has been deployed. So I'm just going to talk about 2 examples very quickly. Here you can see Invinity Infinity's VS3 Energy Superpower Oxford. This is where we have deployed a 2 megawatt, 5 megawatt hour energy storage system in Oxford. You can see our systems all in. These are 20-foot containers, they're double stacked, and these are energized systems, and they are going to be providing energy balancing services to the wholesale grid. So charging at cheap times and discharging when the market needs them at the most expensive times. They'll also be providing really quick services. So they'll be providing sub-second ancillary services to keep that grid frequency within 50 hertz. Moving on to another site we've deployed recently. This is a place in Scotland called Scottish Water, which is a water utility. They want to maximise their use of on-site renewables, and they realise they get a diminishing return with the solar. They want to add on energy storage to take that excess solar and shift it so that their night periods or their shoulder periods in the day are also met by on-site generated low-carbon energy storage. I hope that's given you a taste of what we're doing at Infinity and piqued your interest in vanadium flow.
Thank you so much, Ed. I interviewed Infinity CEO Larry Zulch back in July of 2020. Glad to see you guys are doing so well. Gautam Yadav, Director of Advanced Battery Development for Urban Electric Power. How you doing, Gautam?
Hey, Jay. Just working hard in the labs to make an alternative to lithium ion. So Urban Electric Power, it's based in New York State. It's spun out of City College of New York. We won an ARPA-E grant where the challenge was to create a battery energy storage technology which gives you less than $100 per kilowatt hour. We looked at the entire gamut of the battery chemistry world, and we saw that zinc manganese dioxide, the AA batteries that you buy, like Duracell or Energizer that you use every day, that could be a possible solution, and that AA battery that you buy, it's a primary battery where you just discharge it once and you throw it out. But the energy density is high. It can match lithium ion energy density. And the question was, can you make it rechargeable to that energy density and get that same cost advantage? Urban Electric Power is in the business of making continuous manufacturing of cylindrical cells. This is just one of the lines that we have put up in New York. We have a partnership with an Indian conglomerate as well to serve the Indian market. The manufacturing process is to make these big cylindrical cells. The primary AA battery, we take this and make it rechargeable to a higher capacity. The capacity of the cell is designed to meet different needs, of the applications of the customers. It's a very safe chemistry. Like Dan mentioned, it's zinc-based. Manganese dioxide is something which you can find in dirt, right? It's widely available. It's aqueous-based, and it's non-toxic, and it's very safe. We did this UL certification, just like Dan, for nickel zinc. We got the same certifications, the same remarks that it's essentially safe battery. Unlike lithium-ion batteries, it's essentially non-flammable. The chemistry, I just wanted to talk a little bit about it. It's based on zinc anodes and manganese dioxide cathode. The manganese dioxide cathode goes through different electrochemical reactions to give its capacity. The maximum capacity that you can get is around 617 milliamp hours per gram through two different reactions. So when you look at the specific capacities of manganese dioxide and zinc, it's 600 and 800 milliamp hours per gram. It's way more than any lithium ion cathode or anode which is currently being used. Just to show you an example of what Urban Electric Power is doing, the generation 1 is serving the UPS backup applications. One is this supercomputer center in San Diego, where they have a lead acid battery which is just giving 15 minutes of backup. The zinc manganese dioxide chemistry is able to give you 90 minutes of backup, but at a lower cost, which is substantial, right? And the same footprint. So the energy density is also high. Another application space which we've been targeting where lead acid has been used is solar microgrid applications, where off-grid locations in remote communities like the Navajo Nation in the US, they use lead acid batteries because they don't have access to the grid. Is there a chemistry that can do this? And this is one application which we have found, where a lead acid battery can give you 6 to 7 years of service life. And we have found that the same can be done with zinc manganese dioxide chemistry, especially in the first generation chemistry. The targets for Urban Electric Power is to go from a very low bill of materials cost, $150 per kilowatt hour, to $40 per kilowatt hour in our generation 1. And it's being done through increasing the active material utilization of the cathode and anode and reducing the costs and also the economics of scale which the Indian plant will give. Likewise, for generation 2, we're trying to do the same, but the energy density is increased twice compared to generation 1. And the costs are very low. It somewhat matches to the primary battery when you think of it. When you buy as a consumer, you're paying approximately $30 per kilowatt hour. And that's what a rechargeable battery should come to if you're trying to make it rechargeable as well, right? And something which I want to really touch on is the next future of this chemistry. Aqueous-based batteries like zinc manganese dioxide, the average voltage has been always low, around 1.2 volts. The question has been, can you break this 2-volt barrier for zinc anode batteries. And that's what we have done. We have increased the voltage of the battery to around 2.5 volts, which matches that of a lithium-ion chemistry. So if you really think of it as a perspective, what we have done is now we have increased not only the capacity in this x-axis, we have also increased the voltage. So that means energy density wise, zinc manganese dioxide batteries are going to match those of the future of lithium-ion chemistries. And that's a big thing to be mentioned about for metallic zinc anode batteries. And when you do this, the application space opens up. It's not only grid storage. Now you go into thinking about, for example, electric vehicles. That's where I want to end it and open up the discussions if people have questions. So thank you.
Thank you so much, Gautam. The first question I have is for you. Zinc manganese is widely available. I mentioned AA batteries at the beginning. What have you done to make it rechargeable and available for larger applications like stationary storage? I've done a few zinc episodes in the past. One was at Naval Research Laboratory. Another one, I believe EOS had a similar technology. I think the rechargeability was always the biggest challenge with zinc, right?
Right. Just like any good chef, they don't really want to mention their secret sauce, right? But no, it's essentially chemistry where we have gone in and tuned the crystal structures of these electrode materials like manganese dioxide and zinc. People may not know it's actually more than 100 years old. Zinc anodes was the very first battery to be invented. All we have done is we have looked at this chemistry. What can we do to the manganese dioxide to make it rechargeable? And we have used certain additives and dopants which allow us to do that. Likewise, it's been a clever mix of even tuning the electrolyte, because eventually the third component is the electrolyte, where it's the one which is gluing everything together, if you think of it, right? And that's what we have done.
Ed, I've interviewed Infinity in the past. There are a few different flow battery chemistries out there. In addition to vanadium, we're hearing about iron flow chemistry as well. I'm sure there's others. How abundant is vanadium, and what should we understand about what makes these flow battery chemistries different? Flow batteries are kind of a technology within a technology, right?
Yeah, you're trying to peek into the flow battery space. There's an enormous amount of stuff going on. First, on vanadium, how abundant is vanadium? I think it's the 13th most abundant element, more abundant than copper, zinc, lead. So you've got a huge amount of vanadium that's being mined today to go into standard commercial processes like hardening steel. You almost certainly have some vanadium in your house. You might not know about it, but it's there. On what makes vanadium different to other flow batteries? Now, that's a really good question, right? So on one hand, we have sort of the lithium space, the short duration storage. And then on the other hand, we have this really short duration stuff. Really long duration stuff, you've got hydrogen or combined cycle gas turbine, CCGTs that you see in power markets. And in between, you have this sort of medium duration space where there's lots of energy storage techs that are all fighting for that space and all fighting to prove that they're the kind of right solution for it. And I think there is a very large number of people out there, and they've all got really good techs, and they've all got really good reasons as why they're developing it. What I would say to people looking from the outside looking in, I would look to see it, just the stages of those technologies. It's getting from that sort of early R&D stage of, can you get sort of real prototypes in the factory? Can you mass produce it? Then can you get real demonstrators on site connected to the grid and really making commercial value for your customers? Because crossing the commercial chasm is a really, really difficult thing to do. And so when you see that happening with a company, it's a really positive and a really good sign, and it's hugely difficult to do. What I would say that sort of splits them apart without kind of going into the individual sort of technical details is that kind of maturity of storage.
Dan, you mentioned a little bit about how green the technology is. Your website says that as well. I remember when I was working in the fracking sector, we had a water recycling technology, and I think our marketing guy kind of slapped us down for calling it green. Everything's green, right? Exactly why is it green? And was there any third-party independent analysis of that? So is it green, I guess, is the question.
Yeah, that's a great question, Jay. The battery, because of the fact that everything in it, literally, when you recycle a nickel zinc battery, you recover the nickel, you recover the zinc, you recover the copper in it, you can recover the plastic in the case. Typically, the electrolyte is neutralized. It's a potassium hydroxide electrolyte. It's easily neutralized using an acid to return the pH basically to a balanced state. And really, the waste product that you have from it is the separator material between the plates. We claim 90% recyclability. It's closer realistically to 98%. There are no toxic metals in this. There's no toxic chemistry in it. Everything that we use is something that literally, if you take the battery and throw it in a landfill, the EPA won't even take notice because there's nothing in it that's listed as a toxic material. We don't recommend you do that, however. The materials are worth quite a bit more than just tossing it in a landfill. So you get a good return on your battery. The big end of it, though, if you look look at it and compare to just using lithium, not as a whipping dog, but just basically as a comparison point, we don't have to deal with all of the lithium mining and refining. That's a pretty messy process in the real world. And there are a lot of toxic chemistry used, an awful lot of water in that. And of course, your carbon footprint isn't really good because all of the mining machinery uses fossil fuels. One of the big ends of ours is that we don't have to go directly mine the materials ourselves. I'll be truly honest with you and tell you that our primary manufacturing plant is located right next to a nickel mine, which doesn't hurt me transportation-wise. But the study that I presented is an independent third-party study that differentiator. If you're looking at these technologies and comparing to lithium, virtually everything in the lithium world that we use, UPSs, grid storage, everything else, are energy batteries. Very similar to what Gautam and Ed have. We are a power battery. Completely different end of the scale. Their batteries are excellent at what they do. They are designed for long-term discharge at a reasonably moderate rate. Our battery is designed specifically as a high power battery. Our battery is about the same size as a 330 watt per cell Intersys battery, lead acid. That battery will give you 330 watts per cell for 15 minutes. Our battery has 8 cells in it and will give you 1,000 watts per cell for 5 minutes. We are very friendly economically, environmentally, and power-wise.
All right. Thank you, Dan. I'm going to get to some of the questions from the audience. There's plenty of them. I just have one question from my original list, and is your technologies are new. I know that zinc has been around for a long time, but this application, lithium's pretty entrenched, right? From a business development standpoint, how are you getting customers comfortable with the reliability question, with the idea that you guys aren't going to go away, right? Because lithium has a little bit of an edge there. You guys have so many advantages. How are you getting customers comfortable with you now?
Basically, we go out and present the fact. We have a lot of independent third-party testing that we're able to show them. We don't blow our own horn so much that we have to present only our data. And one of the big things is that we have had a number of presentations to large data center operators. If I mentioned the names, everybody would recognize who we're dealing with. We have very efficiently broken into virtually all of the major UPS providers and all of the major data center hosting companies. It's been a long struggle, but having over 100 years of history with the battery doesn't hurt us at all.
Yeah, I echo what Dan was saying. In terms of reliability, everyone is comfortable using a AA battery in their home. Now we are scaling it up, and I think the more demonstrations we do in the field, the more, publicity is a word I can use here. It gets out. People get more acquainted with the technology. All these things contribute to increasing that reliability and awareness of what the chemistry is about. And I think people are getting more knowledgeable on batteries and what chemistries are doing, So these things are helping in terms of business development. Although I'm not a business development guy, but that's what I can say.
Jay, I'll give you a quick answer. So 3 things. 1, net zero, right? People want to get more out of their renewables. You know how much renewables has to be built over the next 10 years to try and do net zero. Energy storage has to go alongside that. There's a huge mandate from customers to build storage alongside renewables. 2, people are buying proven tech. So people are seeing the systems, seeing them in, they're seeing them running. That makes a huge difference in that sales process. And 3, it makes people money, right? So people looking at a big energy bill, all of a sudden see that they can put solar on, great, that makes them some money, but they can also put on solar plus some more solar and some storage and save even more money. This is the kind of thing that people are seeing all over the place and seeing that business case come to life. So it's an exciting time.
Yeah, there were some questions about energy density, some questions about if they can fit in a storage container. And I think my question on top of that is, if you're doing stationary storage, does energy density really matter as much, right?
Yeah, good question. And look, the answer from doing some of these projects at sort of megawatt hour scale is yes, it does. It's not the be all and end all, but when it comes to delivery costs and it comes to civils costs and it comes to space requirements, when you look at what developers have within their portfolios, it is important. You need to be reasonably energy dense. You can't be taking up acres upon acres of land, but you don't need to be as energy dense as some of the shorter term solutions you see on the market today.
Yeah, you don't have to be lithium, in other words.
Exactly.
The other question I got for you guys was interest in EV and EV charging. I did a guest one time who had a solar-powered EV charging station. I mean, there's certain limits to how much the grid can handle. Maybe you guys would be a good option for all the charging that may be coming online. Again, powered by lithium.
Yeah, we're actually working in that space now using the nickel zinc batteries because of their very rapid response to absorb most of the inrush of the charging station and get the charge level stabilized, and then transferring it either over to a secondary energy storage technology or back to the grid.
For energy storage and microgrid applications, what size and types of transformers match well for recharging? And I believe you also need inverters, right?
You typically have to have the charging technology, and what they're actually talking about here gets into more of a grid-tied storage type application. And for instantaneous response, something like the nickel zinc would be ideal. For longer term things like the flow batteries or zinc manganese would be better technologies. You generally have equipment that's designed specifically to tie you to the grid, both the charging side and the inverter side, and it has to be rated for grid-tied applications. So it's a rather specialized area. It's not something you're going to go pick an off-the-shelf transformer or inverter to make thing work.
Yeah, and Dan, just one thing to that, there's a real locational element to that. So within the US, there's people who have proven and got a good track record in terms of transformers for that grid. You go to the EU, it's a slightly different kettle of fish. And then you go to somewhere like Australia, again, you'll see some of the same names coming back in. It's really important for your storage projects.
And then finally, I've really tried to make a point about this with lithium. And I think this is something that lithium can overcome, but I think that it's something that your technologies can be addressed right now. The supply chain. Lithium supply chain goes all around the world, right? I did a guest where all the lithium they're mining is coming from South America, the Atacama Desert in Chile. Are you able to produce your own battery packs in your own hemisphere? And is that a selling point that you're bringing up? That's the last question for everybody.
Yes. In fact, we are looking to move into additional areas. We're currently manufacturing in Asia, but we have supply chain in both the EU and in North America. We can easily move from one place to another. We intend to, in the long run, produce batteries in the region where they're going to be used. And we are not the only nickel zinc supplier. So if something happens to Zinc 5, there are other people out there that are already working in the nickel zinc arena.
Yeah. I mean, same with manganese, I mean, you have manganese mines in the US. When you think about other countries, they're rich in manganese. And zinc, of course, it's also in the US. Depending on where you set up your manufacturing base, these elements are widely available all over the world.
Yeah, I'm going to echo the other two panelists. So we're at that stage where we have that maturity in supply chain. It's very easy to do within one hemisphere or the other. It's all very possible.
All right. Well, I think that'll do it for the panel. Thank you so much, everyone. And hey, what a great group. This was a great conversation. I think it's hopefully going to open each eyes. And thank you so much, everyone who attended, for your great questions. That was Dan Lambert, Ed Porter, and Gautam Yadav, 3 guests from my panel on lithium-ion battery alternatives recording for the PowerGen Plus virtual series. I want to thank my guests and their teams at Zinc 5 Invinity and Urban Electric Power for their support, as well as Desiree Hansen and the team at PowerGen for setting this up. I can't wait to see you on stage at PowerGen International in person in Dallas in May. You can find plenty of pictures as well as presentations for this panel on energy-cast.com, as well as on Instagram and Parler at Host Energy and Twitter at Host Energy Cast. All guests are sent the raw and completed audio the week of release. So far, no complaints. Be sure to leave us a positive review on iTunes. That gets the word out. Music was produced by Sean Stroop at Stroop Loops. That wraps up episode 130. Be sure to join us next week when we take a closer look at what true demand response looks like. Until then, I'm Jay Downhauer. We'll see you next time.